Okay, in this last video, we're going to be looking at the reactions of carboxylic acids and their spectroscopy. First, let's look at what reactions we previously encountered. All right, so earlier in this course, we showed that we could make primary alcohols like this by reducing carboxylic acids with lithium aluminum hydride. Remember that in this reaction that we cannot use sodium borohydride. It's not strong enough because the carbonyl group is less reactive in a carboxylic acid than it is in an aldehyde or ketone. Okay. We introduced this reaction in the alcohol chapter, and this is the Fischer esterification. If we take a carboxylic acid, like furan carboxylic acid here, and an alcohol like cyclohexyl alcohol, a little sulfuric acid, we're going to generate an ester, okay? And notice how in this ester, we're going to look at, we can divide it into two parts, the acid part here, which consists of the carbonyl group and the adjacent carbon plus everything that goes with that carbon, and the alcohol group, which includes the oxygen attached to the carbonyl group and everything else attached to that particular oxygen. In this section, we're actually going to look at the mechanism for this reaction, and we'll have a deeper understanding why we call it the acid part and the alcohol part. All right. I also want to make you aware that when we present the mechanism, you're going to get two mechanisms for the price of one, because the reverse reaction here is also a feasible reaction when you have lots of water present. And this is called acid catalyzed ester hydrolysis. It's a not a key reaction, but a reaction that we're going to present in the next chapter. And we're not going to present the mechanism. We're just going to tell you that it's the reverse of the Fischer esterification. Okay, and finally, we have this reaction here at the bottom. The preparation of an acid chloride from an acid can be done most commonly with thionyl chloride, SOCl2, making SO2 and HCl as a byproduct. You may remember that earlier, a long time ago, we showed that you can take an alcohol and convert the OH group into a chlorine, and this is kind of basically what's happening here as well. There are other reagents that'll do this. Phosphorus pentachloride or oxallyl chloride are good examples of alternative reagents for converting an acid into an acid chloride. All right, so let's just complete some Fischer esterification reaction equations right here. Okay, so what is the ester that's comes from this carboxylic acid, I guess 2-methylpropionic acid, and cyclohexyl methyl alcohol. Okay, so that ester would be the one here. And remember that this part here comes from the acid, and this part here comes from the alcohol. All right. What's the ester you get from 2-chlorobenzoic acid and butanol? Okay, so the ester that you get is going to be the ester right there. Okay, so let's look at the mechanism of the Fischer esterification, and I'm going to draw every reaction here as an equilibrium arrow, because the only thing that controls the direction of equilibrium is what you do with the water that's produced as a byproduct. Okay, so in the Fischer esterification, you want it to go to the right, so you want to minimize the amount of water. And what's typically done is you do this at a temperature above the boiling point of water, and you boil the water out of the solution as it forms. Okay? If you want to hydrolyze an ester under acid catalyzed conditions, what you want to do is you want to have a lot of water present so that the reaction prefers to go to the left. All right, so let's look at mechanism. All right, so when you first encountered the mechanism here, you probably noticed that in addition to the lone pairs that I gave you, there are a lot of other lone pairs in this molecule. Okay. So it turns out that in a complex situation like this, what happens is that you're actually protonating every one of these sites to reversibly, okay? But it's only when you protonate the carbonyl group, and specifically the carbonyl oxygen right here, that the reaction goes in a forward direction. All of those things happen, but they're sideshows that don't really amount to anything. Okay, so we protonate the alcohol. Protonate the carbonyl oxygen. Now this makes this carbon right here a better electrophile. And so now the relatively poor nucleophile, just the neutral alcohol, can attack this carbonyl like you see here and give you this molecule here that has 3 distinct hydroxy groups on a single carbon, or 3 oxygens on 1 carbon. Okay. Recognize that extra proton that we have on the what was originally the alcohol oxygen could be just as happy on any of those other oxygens. And so we're going to transfer it over here. And what happens here is any of these lone pairs can push out the water. I've just shown this oxygen here doing it. The lone pairs on this oxygen could also be shown doing it. There wouldn't be anything wrong with that. Okay. Actually, and finally, we are removing the extra hydrogen here and reversibly making H3O+. Okay, recognize that all of these steps are reversible, so if we want to take the ester back into its original components, we would write a mechanism where we just protonate the ester oxygen, eject the water group, okay, we're looking at the reverse reaction here. Add the water group, transfer the proton to another place, and eject the alcohol group. All right, so why are we, so another interesting effect here is what happens to the oxygen. All right, so a common labeling tool, or a common mechanism tool that people use here, is oxygen 18 labeling. And let's label this oxygen. What people do to label an oxygen is O18 often is just color in the inside of the oxygen. All right, so what happens to this oxygen? Here it is. Let's keep that one colored. Okay, there it is there. Okay, here it is right here. And here it is here. And here it is in the final product, okay? All right, so that's why we call this, of course, the alcohol part, because all of those atoms come from the alcohol. And these are the atoms that came from the acid. Okay, all right, so let's look at another reaction. This is unique to what we call beta-oxocarboxylic acids. As long as we have some sort of carbonyl group in the beta position relative to the carboxylic acid group, we can thermally decarboxylate. Heating this to a temperature usually 120 degrees or higher, I just arbitrarily say 150 degrees, actually ejects carbon dioxide from the molecule. Okay, so carbon dioxide is produced from these two, and the net result is that this hydrogen ends up over there. But let's look at how that process happens. So here's the mechanism. We're going to orient this molecule, do a bond rotation here, so it's now in this conformation where the hydrogen is near the oxygen, and this is probably the favored conformation because of the intramolecular hydrogen bonding. All right, we're going to now do a paracyclic reaction that's basically like the Diels-Alder reaction, where we push 3 arrows, and this gives us now the enol and carbon dioxide. And remember that from the alkyne chapter, that enols are in equilibrium with ketones and aldehydes, but the equilibrium heavily favors the ketone. Okay, so this enol is now just going to spontaneously convert to that. So this, I've shown this as an equilibrium, but it really it's like a 99.9 to 1 equilibrium. My reverse equilibrium arrow is way too big in this equation. Okay, all right, so let's look at some sample equations. This is malonic acid, a very important acid in biology, and at 150 degrees it readily decarboxylates to give you acetic acid. It doesn't matter what type of carbonyl group you have, it can as long as it's in the beta position, it can be a ketone, aldehyde, ester, carboxylic acid, amide, anything, any C double bond O in the beta position will enable this reaction to occur. So at 150 degrees, this carboxylic acid that you see here will lose CO2 and give you cyclohexanone. Okay, let's just do a problem here. Circle the compounds that can lose CO2 if heated to 150 degrees C. All right, so what we're looking for is carboxylic acids that have a C double bond O on the beta carbon. Okay, all right, so this one has only one COH group, or only one C double bond O of any kind. We're not going to circle that one. All right. This one has an alpha C double bond O. This one has a beta C double bond O. And this one has a gamma C double bond O. So we only select the ones that have the beta C double bond O's, and each of these compounds we could reasonably anticipate that if we heated them to a temperature not all that high, that we would lose carbon dioxide from these molecules and get the decarboxylation product. Okay, we're now going to look at spectroscopy of carboxylic acids. We've already been introduced to the OH group in the alcohol chapter and the C double bond O in the ketone aldehyde chapter, but the interplay of these groups leads to a few differences. Okay, so first let's look at the infrared. We're going to find that the peak is extremely broad, extremely intense OH stretch, far more intense than in an alcohol, and it covers a huge range, okay, more than 1,000 wave numbers in the spectrum. Okay, we also so there's our OH stretch. We also have a C double bond O stretch, and this is very concentration dependent absorption, because if there's a lot of hydrogen bonding, it comes at a relatively low frequency. If there's not very much hydrogen bonding present, it comes at a higher stretching frequency. Okay, and just like before with the aldehyde and ketone carbonyl groups, we find that conjugation is going to cause the carbonyl stretch to go to a lower value, and electron withdrawal will shift the peak position to a higher value. So here is just a average carboxylic acid with an alkyl group. cyclohexane carboxylic acid, we find that the C double bond O comes at 1706 wave numbers. All right. Now, we're going to replace the cyclohexyl with a phenyl. This means that it's now conjugated, and what we see is that the stretching frequency has dropped a little. All right, we're going to now load the benzene ring with electron withdrawing fluorine groups, and what you see now is that it's dropped it's increased now from 1696 to 1720 wave numbers. Okay, let's just look at a spectrum for a carboxylic acid. This is pentanoic acid, and this is where I'm getting these spectra. I don't want to commit any copyright violations. They say they were cool if we would just acknowledge it, and I'm not getting any money for these videos, so this is clearly a non-profit situation. All right, so here is our OH stretch. Okay, notice how our OH stretch is taking up a huge part of the spectrum. In fact, it's so huge that it's starting to overlap with the CH. The CH is just a little pimple on the OH stretch here. And of course here is the C double bond O stretch. One of these is over here, might be the C single bond O stretch, but this is kind of an unreliable absorption. You can't really count on assigning that band accurately. Okay, so you do see something down there usually because of the CO stretch, but it's hard to just pinpoint it to a specific stretch. Okay, all right. Let's look at the NMR properties. Okay, one of the most characteristic properties of a carboxylic acid is that the OH is going to come at a very high value, 11 to 15 parts per million. And it's usually very broad. Sometimes it's so broad that it'll just barely be visible. Okay, and we know that this proton that's adjacent to the carbonyl group, just like in the ketones and aldehydes and in the benzene rings, comes at a little higher value than normal alkyl group protons, typically 2 to 3 parts per million. All right, another important distinction here is that in the C13 NMR, the C double bond O of a carboxylic acid and any carboxylic acid derivative like an ester, an amide, or an acid chloride comes in a different range than the carbonyl carbon of a ketone or aldehyde. And the ketone or aldehyde groups always come at 190 to 220. So there's this kind of dividing line between 185 and 90 where everything below 185 is a carboxylic acid derivative, and everything above 190 is a ketone or an aldehyde. And there's not that many carbonyl groups that come between like 185 and 190. It's actually a very reliable assignment. All right, so most of the spectra that you've seen go from 0 to 10 parts per million. And what we see here is that we're looking for a proton that comes outside the normal range. So here is, 3-methyl butanoic acid, 1, 2, 3, 4. Yeah, 3-methyl butanoic acid is this compound. And what we see here is that our OH comes at a very high number. We had to extend the scale beyond where we normally extend it. When we extend it this far, the other peaks have become so small that it's hard to tell the difference between singlets, doublets, triplets, or whatever. So what we have here is that this is a doublet, 2 hydrogens. And of course, it goes to these 2 hydrogens here. This is a doublet, 6 hydrogens, and goes to these here, and this is a nonette. There's no way you could see that. actually. And actually, that looks like a girl's name there, actually. Not Nonette, that's how you would spell that. Sorry. Okay. All right. So anyway, this is one hydrogen, and it comes, and it's this hydrogen right there. What you notice here is that this hydrogen here comes a little higher than all of the others because it's the one that's right adjacent to the COH group. All right, so we're going to end this chapter with a matching problem. So this is a multiple choice. Which structure goes with the spectral data? Okay, so there we have the picture of the infrared spectra, the picture of the NMR spectrum, and a list of the C13 peaks. So we don't have a picture of the C13, we just have a list of the peaks. All right. What can we tell here? Okay, you probably figured out that it's a carboxylic acid because we're in the carboxylic acid chapter, but this super large OH stretch is a dead giveaway. This is also a dead giveaway, the fact that we have an OH peak coming at almost 12 parts per million. Okay, so this is a carboxylic acid. We don't need to consider the choices that are not carboxylic acids. All right, so when we look at the coupling pattern, it's 2 hydrogens triplet, 2 hydrogens a triplet, and 4 hydrogens a multiplet. All right, so if you look at the uniquely high chemical shift here, this would be a triplet 1 hydrogen. This would be a triplet 2 hydrogens. So it looks like this is really the only logical choice here, okay, for the compound, okay? This is also 2 hydrogens, triplet 2 hydrogens right here. And these other 4 hydrogens, they're not well separated. They're very similar in where you expect their chemical shift to be, so they exist as a multiplet. Okay, so that's where this carboxylic acid chapter ends. The next chapter, where we talk about carboxylic acids, has some fundamental relationships to this chapter. We're going to see some similarities in the spectral properties, and we're going to see that a carboxylic acid is potentially a precursor to all of the compounds in the next chapter.